Today we see the laboratory 1, which comes with 2 parts. Why 2 parts? The first part is a summary. It's a revision of Python that I'm not going to do with you in class. You have previous years, first year exams taken from previous years of computer science course on Python with one possible solution, maybe not the best one, maybe not what how you would do it, but still one possible solution. You should do this when? You should do these exercises if you don't feel proficient with Python, if you don't remember how to use Python, if you are rusty, or if you didn't get a good mark and you didn't use Python for several years. So in that case, revise and try to do them. If you are proficient with Python, you remember everything, you were using Python for 15 hours per week for the whole previous semester, then probably you don't need to do this. But that's up to you to know whether you need it or not. You have it. You have solutions. If you want to ask me something about this, come here and I will answer you. Otherwise, I will just skip these exercises. Then we have part 2, where we start with the libraries. For today, we need to start directly for the next laboratories, typically, with the exception of next week, but for next week it's already slightly less relevant. The laboratories will not come the day after the corresponding lecture, but will be the next week. Since we can't afford to lose weeks because we are already losing 1 week to holidays, we can't afford to, so we don't have any spare days left. We start directly this week with the numpy, even if we saw it just yesterday. Typically, this will not happen. Typically, you will have 1 week in between to revise the theory and then do the laboratory. For this week, it was not possible. So I know that you may not be proficient yet. That's also why I will go through the solution so that you can revise it after you have done it at home if you don't manage to do it now. What you are supposed to do here is to start practicing using numpy. We have 3 exercises. 6 and 8 refer to the first part of the laboratory. They just ask you to solve 2 of those problems using numpy library to represent matrices. These, of course, have nothing to do with machine learning. I chose those 2 exercises just in case if you want to do also the first batch of problems, so the revision of Python, then you can see how we would translate from going from how you were representing lists in the first year course to what we do when we use a library like numpy. So for this reason, they are the same exercises with some modifications, slight modifications, but solved with numpy. And then exercise 7 is what we will do today here, which essentially is a set of operations on numpy arrays that will allow us to start working with these objects, to start seeing some connections of what we saw yesterday about the potentiality, the capabilities of the library and how to use it. Now, as I said already to your colleagues before, you have solutions to all these that come in different flavors. Why is that? Well, it will be more clear when I explain the solution, but let me just say now that we will see a naive solution together. That is what I expect you to be able to do now or shortly. Maybe not today because, as I said, you didn't have time to practice, but shortly to work with the libraries. Then we will see how you would actually use library in real life. The way you will write code today probably looks nothing like anybody who's using these libraries in a real world would write the code. So we'll see how to write it in the numpy framework, in a flavor that makes sense in that framework. Why we need to do this? Well, for 2 reasons. You are not expected to be able to write that code even at the end of the course. You may be able to do. You may not. I don't care too much that you are able to write the code because this is not a course on learning how to properly use the libraries. But the problem is, as we said yesterday, for some algorithms, if you don't do them efficiently, you will have issues when running them on the project data. And if the project data was not, to avoid these difficulties, I would need to reduce the size of the project dataset, but if I were to reduce the size of the project dataset, it would become so small that most of the analysis wouldn't make much sense anymore. So to have enough samples that the analysis makes sense, we need the dataset to have at least a reasonable size. This reasonable size may be already too much for what a naive implementation of the algorithms can handle. For this reason, we said yesterday, we will try to put some optimization in the code. In any case, you will get as a solution for the laboratories an efficient implementation of the code that you may study if you are not able to write your own, or if you are able to write your code maybe even efficiently, but you just don't get the algorithm right, so you don't get a solution that works in any case. That may also happen. You have bugs that you are not able to remove. These solutions are written exploiting tricks and exploiting the library capabilities that allow us to have an efficient solution. Since you may need to study this for the exam in case your implementation is not good or is not working, for that, to read them, you must be able to understand what's going on inside. Since we will be using tricks and things to speed up computation, there will be comments that explain you how these tricks work, but you need to also understand how the library works to actually being able to understand why things done in a specific way are actually giving you the result that you were asked to compute. So for this reason, I expect that some things that we do as optimization may not be something that you are able to write at the end of the course, but that you are able to read. You must be at least able to read and understand what's going on, okay? So we start already today seeing some of these solutions to start familiarizing with the tricks and the capabilities that we need to actually understand, well, the properties of the library that we need to understand what's going on. Just to give you a short example, then I let you work. Exercise B, written in a naive way, is this. Exercise B, written as you would do in numpy properly, is this. The second solution is faster, well, from the point of view of memory, probably it's not more efficient, it's pretty much the same, but it's much faster. It's much faster to write because it's much shorter. It's much faster to maintain because the number of bugs that I can make in 8, 9 characters, well, they are more limited than what I can make in 10, 12 lines of code. Once you know how the library works, you can read that line and already understand what you are trying to achieve from a higher level point of view. What was the task that I gave you if you are able to read what this line of code is doing? So for this reason, I will explain today how to reach this. You are not supposed to write this. You are supposed to be able to write this, because this is essentially first-year course with numpy arrays in place of the list of lists representation of matrices. But from the point of view of the logic, the for loops and so on, there is nothing new with what you should already know. And together we will, during the course, we'll try to switch towards these kind of things. In each laboratory, we will reintroduce the things, so don't worry if you don't get everything today. This will be reintroduced also laboratory by laboratory when we use them. So it's not like you don't understand this today, that's over. This, we will reuse it several times and we'll introduce it in the laboratory saying why we do it in that way and how it works. But it's better if we start already to see it today. So the idea here is I let you work for like 20, 25 minutes on your own, and then we go through the solution. What you manage to do, that's good. What you don't manage to do, you can always try to do at home and then check the solutions online again. We have the recording. Okay, questions? Okay, then you can start working. Okay, so as I said, I don't have the time to let you work more on your own before we see the solution. So I will now go through the solution. If you want, you can recheck the explanation afterwards when you have done the rest of the exercise on your own at home. But I want to introduce some things that we will need for the other, as I said, to understand Python code a bit, NumPy code a bit better. So let's go back to the exercise at hand. It's laboratory 1, exercise 7.A. Write a function that, given two integers m and n, returns a two-dimensional array, which is a matrix with m rows and n columns. Data type must be float 64, and the matrix must be built so that in position ij of the matrix, I will find the value I times j, where I is the index of the row and j the index of the corresponding column. So, for example, this kind of object. Okay, one possible way that we may have implemented this that I will not discuss is the trivial method where you just take you build it as a list of lists and then you pass it to numpy.array to create the matrix. This is the least interesting one because that doesn't add anything to our knowledge on NumPy except that if you pass a list of lists to the constructor, it will create an array. So let's start with a solution that works directly with NumPy, so without going through the list of lists solution. This means that we need to think as we were doing in C. We want to create a matrix, so we start creating an empty object that will contain our elements, and then we fill it. How do we create an empty matrix? We can't create an empty matrix in the sense of empty lists in Python. We need to create a matrix whose values have no actual logical meaning. When we create an array, we need to reserve also its memory, as you would do in C. How would you do this exercise in C? You would create an array which contains n times n cells of type double, and then you would fill it. With NumPy, we follow the same strategy. We start creating an array which has m rows and then columns, which initially will be filled with values that for us can be anything, because in any case we will override them, and then we fill the values of the matrix with what we need. How can we create the initial array? Well, one possible way, since we don't care about the elements, let's decide that we fill it with zeros at the beginning. That's one possible initialization for our array. How can we create a matrix m times n with zeros? We have function 0 for the NumPy module. We pass as first element either one integer, and then it will create an array with, so if I pass an integer, it will create an array with one dimension and elements equal to 0, or I pass a tuple, and then the tuple is interpreted as the shape of the array that I want to create. So in this case, it will create an array with shape m, n. So m rows and n columns. So this will be the shape of the array that is created. We want the array to have doubles, so float 64 in the NumPy naming. We can pass the type arguments. It's a keyword argument, but well, we can pass it as a position if you want as well. But we set it to numpy.float64. This is not necessary in the sense that by default this will be a NumPy array with floats. So if let me remove this. If I create an array of zeros, by default it will be of type float64. In this way, we ensure that even if we don't remember what is the default type, the type will be float64. So here we put it just in case to be sure that we get what we want. Then I have my array M, which is a matrix of small m rows and small n columns. In the example, it was 3 times 4. And now I need to fill it. How do I fill it? Well, naive way, 2 for loops that iterate over all the cells of the matrix. Each time I get the indices of one cell, I fill it with the corresponding value. So I have, for example, an external for loop on rows. I can reverse the loops. I can loop first on columns and then on rows. Here we have external loop on rows. I will be the index of the rows. I need to iterate with over the row indices. The row indices will go from 0 to m minus 1. If I have 3 rows, I need to loop on indices 0, 1, and 2. These are the indexes of the rows of the matrix, 0, 1, and 2. And let's put the indices also for the columns of the matrix. So for loop that will run over the rows, and then internal loop that runs over the columns. So given a row run over all columns, the columns are n, so j in range of n will iterate 0, 1, 2, 3. When I'm in the inner loop, I have that I refers to a row index and j is a column index. In position ij, what should I put? I should put the value I times j, so I compute the value I times j, and then I want to store this value in the matrix. How do I store it, this value? I store it in position ij. How do I access a single position inside a matrix? Well, I give the index of the column, of the row, and the column, separated by commas. Notice that this is direct indexing, so m of ij refers to a single scalar value inside the matrix. If it's on the left, on the right of an equal, this is a scalar value extracted from the matrix. On the left, it means that in position corresponding to that scalar value, I should put what is on the right of the equality. So I will actually fill matrix M with the products ij for each component. Notice that here I have a scalar, here I have an indexing that refers to a scalar. We have seen yesterday that if we use scalar values for the indices, then these correspond to scalar interpretation of the cell of the matrix. What do I mean? If I have a matrix M, let me just do a bit better matrix M. If we have a matrix M like this one, let's see, yeah, okay, like this one, M of 0, 1 corresponds to a scalar. Why? Remember that every one time we use an index, a scalar value for the indexing, we are getting 1 dimension less in the output. Here we're using 2 scalars for the rows and the columns. The result is a value that has no dimension associated, so it's just a scalar, the value 2.0. Notice that this is just a parenthesis. This is different from doing something like this. This will get exactly the same value, but as a 1 times 1, sorry, as a 1 times 1 matrix. Here I'm taking a slice that goes from row 0 to 1 excluded, from column 1 to 2 excluded, so it's only row 0 in column 1 actually if you draw it, but as a slice, so we keep the associated dimension. So it's a 2 times 2 matrix. If I mix, what I get is a 1-dimensional array. So if, for example, the row index is a scalar, I get a 1-dimensional array. I'm getting row 0, so I'm dropping the row dimension. There is no row dimension anymore. There is just the dimension that was corresponding to the column. And the same if I do the opposite. If I write a slice for the rows and an index for the column, sorry, for the columns, an index, I keep the row dimension, but I lose the column. Result, 1-dimensional array again. Okay? For our case, here we have on the right of the equal a scalar. So on the left, we can use a slice, we can use a scalar, we can use whatever it wants. Here we use a scalar indexing, so the single scalar will be overwritten with the scalar value I times j. If I were to write something like this, it would still work. This would be a slice. It would still work because this would be broadcasted to a 1 times 1 matrix that then is compatible with this 1 times 1 view of the matrix on the left. So there are different ways of doing the same things, but the reason they work are different. The result is the same. But to understand why this works the same as this, to really understand what's going on, you need broadcasting because you need to transform this into a 1 times 1 matrix, which is then copied over the 1 times 1 matrix corresponding to the view that I have on the left of the equal here. And these clauses are the parentheses. So ij just refers to the single value. I put my I times j there. And that's it. If now I call this fx with 3 and 4, I get exactly the result. Each element, row 2, column 3, the result is 2 times 3. Of course, row 0, everything is 0, column 0, everything is 0. Everything gets multiplied by 0, so it remains 0. Okay, now why we don't like this? We don't like this because now imagine that m is equal 10,000, n is equal 10,000, and you need to call this function f 1,000 times in your code. If you do it with for loop in Python, it's not much. If it's written in C, this is 100 million operations, and that's 100 billion operations, something your PC can handle easily in a few seconds if we just see them as low-level operations. But if you do that in Python, you will need to go through the virtual machine for any of these operations, and it will take lots and lots and lots of time to do this computation. So in real life, you don't do this, because if real life requires you to solve problems of this size, they are perfectly affordable problems that you can't solve directly using the Python language in a naive way. For this reason, we exploit numpy. Why? Because numpy, the more operations we can hide inside the library, the more the number of operations that will be executed in C directly, so with low-level instructions that are much more efficient, because the low-level instructions just need to modify the actual memory in the PC. Don't need to go through all the machinery of the virtual machine to actually understand what is the next instruction to process. So the more we can hide inside the library, the more efficient our code will be. So sometimes, like in this case, we will see that we will combine the capabilities of the libraries with tricks that require a bit of reasoning to understand how we can actually represent the same problem in a way that can be readily solved by exploiting what the library is good at doing. The library is good at manipulating arrays. So we need to transform all this problem into a manipulation of arrays where all the loops happen inside the instruction that manipulate the arrays and not explicitly at the Python level. Of course, this requires some reasoning that I don't expect you to be able to do on your own at the beginning of the course. I expect you to be able to understand these kind of reasonings once we show them and we give you an explanation of how they work. Then we expect that you are able to understand how they work. But at the beginning, they may look a bit strange. This one is already quite complex. We will get to a very simple solution, which is quite complex to understand how we get there. To get there, we need to reformulate our problem. How? Well, let's see what we have to compute. We have to compute a matrix M. Let me write it in this way. A matrix M whose elements are what? In position I, j, I need to multiply the index I of the row with the column index j. Now let's imagine that these indices are stored in arrays. And let's see how we can represent the operations from the point of view of arrays. We need that we do what? Well, let's look at the output matrix M. Let's look at the columns of M. The first column of M will be what? It will be 0 multiplied by 0. Let me write it in this way. It will be 1 multiplied by 0. It will be 2 multiplied by 0. Okay? Let me write it in a more compact way. It's the same thing. It will be 0, 1, 2, each of them multiplied by 0. The second column will be what? 0 times 1, so I take 0 and multiply it by 1. Then 1 times 1, I take 1 and I multiply it by 1. Then 2 times 1, I get 2 and I multiply it by 1. Okay? Third column, I do what? 0 times 2, 1 times 2, 2 times 2, and the same for the last. What do I have here? I have that the solution can be represented as this matrix A, let's call it A, which contains what? This vector of indices replicated over the columns, which is then multiplied. Each column of this matrix is multiplied by different value. We'll see how to do that in a moment. So if we are able to cast the problem in this way, we can start building this matrix A, and then we just need to find a way to multiply each column of A by the correct value. Okay? How can we build our matrix A in an easy way? Suggestions? Let's call this vector X. Now there is a method that we didn't see yesterday that is called repeat, which will do exactly this. If you provide a vector with shape, you provide the axis and the number of repetitions. So if you provide a column vector like this and you tell it to repeat over axis 1, it will repeat it over axis 1 n times. But we didn't see this yesterday, so let's not rely on things we didn't see. Let's do it with what we saw yesterday, because it's still doable. Then when we need, we will introduce repeat in the laboratories in any case. So we will discuss how repeat works when we use it. But we don't need to use this repeat. We want, with what we achieved yesterday, it's not the most efficient way of doing it yet, but with what we achieved yesterday, we want to implement this step of replicating this vector X over the columns. How can we do it? Okay, so if you already saw the answer, that's not... Well, let's imagine that I have a matrix of all ones like this with the same shape as my matrix A. What happens, and then we will see that we don't need this matrix actually, but again, let's do this in step. What happens if I multiply a column vector X by this matrix in Python? So I have column vector 3 times 1 times matrix 3 times 4. What does it do? Logically, let's reason it logically. It doesn't do this really physically inside the memory, but logically, we said these directions are different, so my 0, 1, 2 gets replicated 4 times over the axis 1, so the row columns. Inside the memory, it's never building this matrix explicitly unless it's what we need at the end, but it's doing the results of what I would obtain if I were replicating the matrix. So for convenience, we will always say it replicates the columns, then the implementation doesn't do that for real, because it doesn't need, just needs to play well with indices of the arrays without actually needing to replicate. But to understand how it's working, it's easy to think of it as it's replicated in the memory and then multiplying these two. These now have the same shape, element-wise multiplication. if I have matrix A times a matrix of all ones, what is the result? Element-wise multiplication. Each element of A is multiplied by 1, so the result is exactly A. So what I get, thanks to broadcasting, I get my repetition. So I built this matrix A that I wanted to build. Notice that if I exploit broadcasting, I can achieve the same thing. If I take X, it's not in the solution, but if I take X and I multiply it by a row, and this, or one-dimensional, because we've seen that with broadcasting, one-dimensional arrays behave like row vectors when they are mixed with two-dimensional arrays. But if this is a row vector and I do this multiplication, what happens? I have a 3, 1 here. I have a 1, 4 vector here. Broadcasting rule. Number of dimensions is the same, so we don't prepend any one on anything. 1 against 4. Let's keep some more space. So it's 1 against 4. Means that the one that is 1 must be repeated 4 times to match the other one. Then I have 3 against 1. The one that is 1 must be repeated 3 times to match the other one. So implicitly, it's as if it was building this matrix and then doing the product. So what I get is, again, exactly this matrix. And I don't even need to build my matrix M. But for the solution that we see, we build matrix M because that's convenient for the following steps. So now we build our matrix A. We need then to multiply each column of this matrix by the corresponding column index. What does it mean? It means that I take my matrix, and then I need to do what? The first column must be multiplied by 0. The first row of the first column by 0. Then here I should also multiply by 0. Here I should also multiply by 0. Okay? Then here I should multiply by 1. Here I should multiply by 2. And here I should multiply by 3. Now let's build it row-wise. Here I multiply by 0. Then by 1. Then by 2. Then, sorry, this is 1. Then by 3. So let's look at these values. What am I doing? Well, it's as if I was taking A, and then each element of A gets multiplied by what? Let's write just the elements that are multiplying, that are on the right of the equal. These are the elements. If I do this element-wise multiplication, I'm doing exactly this kind of computation. But this is what? These are the column indices interpreted as a row vector that is replicated 3 times in my matrix. So if my indexes, column indexes were written as a row vector, I see that that row is replicated 3 times in this matrix. I call this matrix B. So if I build matrix B that contains the replication of this value 3 times, then I can just do A times B. How I can do it? Well, one possible way is, again, matrix of all ones times row vector that contains value from 0 to 3. But we don't really need to do this matrix. Why? Because when we do this multiplication, the broadcasting already happens naturally. So we don't need to explicitly do it. If we take this matrix A, and we have here a row vector with 0, 1, 2, 3, what happens when I multiply them? Broadcasting, this is 3 times 4, this is 1 times 4, same number of dimensions, so no prepending of ones. 4 is the same, so I keep the columns as they are. 1 against 3, this is not the same, but 1 is 1. So the one that has 1 element, that element gets replicated 3 times. So broadcasting is doing for me this repetition of the row of this vector. Essentially, when you have a matrix multiplied by a row vector, you are multiplying each row of the matrix by the row vector. When you have a matrix multiplied by a column vector, then you are multiplying each column of that matrix by that column vector. So if I have this matrix that is already half of the problem, and I multiply by the row vector with the indices, I get exactly what I need to achieve. So if we look at the code, this is exactly what's happening. I first create my matrix of 1, then I create the column array that contains the value, so my matrix of 1, then the column array that contains the indices of the rows. Notice that it's a column array, but it has the row indexes. So pay attention that row and columns, row indexes in this case are contained in a column vector, because the vector is a column, but the elements correspond to the indexes of the rows. X times M is the matrix that we called A. And then we need to build the vector, row vector that contains the column indices. These are row vector because it has 2 dimensions. You see 2 square brackets. So it has 2 dimensions, so it's a row vector. If I multiply this by y, I get my solution. Okay? Now, question is, can I make it better? Well, element-wise, product is commutative. There is broadcasting involved, but even through broadcasting, we can show that it still remains commutative. So if I exchange the order of the operations, I still get the same results. Now, what does it mean? That here I'm doing x times y all multiplied by m. M is a matrix of all ones. What happens if I do element-wise multiplication with a matrix of all ones? Well, if x times y, if what's on the left here, if this is a matrix with the same shape as m, I get the same results as output. If I multiply a matrix by a matrix of all ones, I get the original matrix as output. I may not get exactly x times y, because if x times y has a different number of dimensions than m, then I get the broadcasted version of x times y. So it's not exactly the same as saying x times y times a matrix of 1 is equal to x times y. That depends on the shape of, so if I have matrix A, if I have A times m, this is equal to A if A is a matrix of the same size as m. If A is, for example, a scalar, the result is not equal to A because the result will still be a matrix. But if A and M has the same shape, then multiplying element-wise by a matrix of 1 doesn't change my result. But x times y already have a matrix, so we don't even need M. We can just compute x times y. Why we can just compute x times y, and why does it work? Because essentially all we have said today, if I write x times y, is done implicitly by the library. Remember that we said we want to build matrix A, which replicates the column indices as, the row indices as columns of matrix A. Then matrix B contains the column indices in its rows. So it's a matrix whose rows correspond to a replicated version of a vector that contains the column indices, okay? If I have this vector x and this vector y, and I multiply them together, then what I have? I have x 3 times 1, 0, 1, 2. Y 1 times 4. How broadcasting works if I do it in this way? Same number of dimensions, so no prepending. Then I need to check dimension by dimension. Here I have a 1 and here I have a 4. They are not the same, which means this vector will be replicated along axis 1 4 times. So logically, this is what happens when I check the first dimension. Then I check the second dimension. Here is 3, and here is 1, and in x is 3. So y gets replicated 3 times along that direction. Broadcasting is building exactly those matrices A and B that we were building explicitly before. And then element-wise multiplication happens logically between these two matrices. So what I get is exactly the matrix which has in position I, j, the product of the index of the row I and the index of the column j. That is what you already saw. Yes? Now I will say. Now, this is what we saw before. Actually, let's put everything together. We first build vector x as a column vector, and then we build vector y. For vector y, we said we need a row vector. But for broadcasting, we say that if it's a row vector or a one-dimensional vector, it wouldn't change. So in the example, we saw x as a 3 times 1 and y already casted to a 1 times 4. But if I were to create y as a one-dimensional vector, so 4, and that's it, what would broadcasting do in this case? It would first prepend a 1 here, so it will transform my y in a row vector, and then whatever we said before would happen. So it would replicate y 3 times and replicate x 4 times on the columns. So we don't need to put it as a row vector y because that's what broadcasting will give us for free. But my strong suggestion is that to be sure, if you want it to be a row vector, you cast it as a row vector so that you are sure you're doing the right thing. So here we don't use it, but in all the code that I put for the solution of the laboratory, or essentially almost all, maybe I forgot somewhere, but almost always, if it's meant to be a row vector, it will be reshaped as a row vector so that we are sure that we see that we want a row vector there. Yes, it's just for safety. If you know the library, you don't need it. It's going to do it on its own. But if you do it, then you're sure that you're doing the right thing. You remember that it's a row and a column. So you have on 1D, you know, here I need a row, I reshape it as a row. Here I want to interpret it as a column, I reshape it as a column. Actually, we will just write a function vcall that will just return the call version of an array, and vrow that does the same. So we don't need to call dot reshape every time. We will just take, rather than x, column vector of x, and rather than y, then row vector of x, we will just call it this way. We will see it next laboratory this way. We won't call reshape because that's more difficult to read if I always have this reshape. While if I have of x times vrow of y, this is easy to understand. I'm doing column version of vector x times row version of vector y. Why is it more safe? Also because maybe I don't remember what is the shape of y. Was it a row vector? What is a column vector that I get as input from another? Maybe it comes from another function. I know that it's logically just a collection of values. But did the function give me a row vector? Did the function give me a column vector? Did the function give me a one-dimensional vector? I know that I need to treat it as a row, so I transform it into a row. Whatever the previous function gave me, my code will work correctly. We saw yesterday that if I expect this to be a column vector and I use it as it is, while the function gave me a one-dimensional vector, this can be very wrong without me even noticing. So it's for safety. Whenever I manipulate something that I'm not 100% sure what's its shape because I don't know where it comes from, and when you write lots of code, you don't remember everything that you wrote before exactly as it was. So you may make assumptions that are not what you did in the previous code. It's easy to make this kind of mistakes. If you cast, you're always sure that you're doing the right thing. Let's say cast. It's not a real cast, but you convert it to what you need, to the shape you need, so that similar compatible shape that have a different meaning get converted to the right version that you need for that specific part of code. Okay? Okay, and side note, here we build the vectors of indices with a range. Since a range returns integers, we cast one of the two arrays to float, then we have integers times float, 64. The result is float 64, so it already takes care of doing the cast. We could have done everything in integer, then cast the result. We could have created both as float 64 arrays, but here is one example of how we can do it. Questions on this one? Okay, then let's see the second one. This is also interesting, so I hope we can see it properly. Second one requires us to normalize a matrix. In which way? We have a matrix which contains elements that are all assumed to be, in this case, greater or equal to 0, and ensure that the sum of the elements on a column is greater than 0, and then we want to normalize the column so that each of them sums to 1. This is something that we will do in laboratory 6 or something like that, so exactly this operation is something that we will need to do later in the course. So for example, we have this matrix, 1, 3, 1, 2, 4, 4, and so on. The sum of the elements of the first column is 5. The sum of the elements of the second column is 10, and so on. So I want to divide all the elements of the first column by 5, all the elements of the second column by 10, and so on for the remaining columns. Okay? So nice solution. I can run a loop over the columns, then for each column I compute the sum of the elements on that column, then I re-loop on the rows of the matrix for that column to normalize them, and it's done. We do it slightly different because that's more tuned towards what we want, how we will do it at the end. We split the problem into two steps. First, we compute the whole set of values that corresponds to the sum of the values on each column, and we store them somewhere, and then we use them to normalize the matrix. So rather than computing the sum on each column and normalizing directly the column, we first compute, in this case, 4 sums for the 4 columns, and then after we have the whole set of sums, the whole collection of sums, we will renormalize the matrix. So first thing that we need, and we also need to create a new array. How do we handle that part? Well, that part is fairly easy. Since we want to create a new array, we take our input matrix M, we call numpy array over M. This creates a copy of M, and we assign the copy to the same variable. In this way, we lose any connection with the original array that was passed to the function. We always work with the new one. We don't even have the possibility to access the M that was passed originally, because we lose the connection to that when we assign M. So we're sure that we're going to work on a new array. If I wanted to modify the original array, I would just delete this row. Now, we need to compute the sum of the elements of each row. We start doing what? Well, we need somewhere where to put these values. We said we first find all the sums, and then we use them. For this, we use an array. Array which should have what? Well, it should have 4 elements because we have 4 columns. Should we do it as a one-dimensional, as a column, as a row vector? Well, we don't know yet. For the moment, we don't have to associate any meaning to this array in particular, except that it collects the values of the sums. So let's make it one-dimensional. Then we will reshape it if needed. So an array, we initialize it with 0 because we know that when we compute summations, the accumulators must be initialized with 0 for the summation to work. We will use the array itself to compute the accumulations directly without any additional variable. So we initialize it with 0. We want an array with a number of elements equal to the number of columns of M. How many columns does M have? M.shape gives us the shape, the tuple with the number of rows and columns in this case, because it's a 2-dimensional array. The second value is the number of columns. So this will create an array with 4 zeros for our input matrix. Then I have my matrix. I want to compute for each column the sum of the element of that column and store it in the corresponding element of this array. So I loop over columns. Again, loop over columns. Where do I take the column information? M dot shape of 1 is the number of columns. So col idx will take the values corresponding to the column indices for this matrix, 0, 1, 2, 3. Each time it will refer to a different column. For each column, what should I do? I should iterate over the rows of the matrix to sum the values that are contained in that column. So I have a loop over the rows of the matrix. At each iteration, I'm considering column col idx and then iterating over the rows. I accumulate the values where in the element corresponding to this column in the array of sums. So array sum of col idx is where I want to accumulate my values. So I take each value and I add it to the position, the element in position col idx of the array of sums. So in this case, I start with 0. When I see the first element, I will accumulate 1. Then I will add 3. This will become 4. Then I will add 1. This will become 5. Then I will move to the second column. Row 0, I add 2 to this element. Then I add 4. This becomes 6. Then I add another 4. And this becomes 10. And so on. Inside this array, I have accumulated the sums of the elements of each column. Then I need to normalize by matrix. I need to again run over all the elements of the matrix. Here it doesn't matter whether I first loop over rows or first loop over columns. The only thing that matters is I loop over all the elements, and whenever I'm seeing element in position ij, I need to divide it by the sum of the elements of column j. So whenever I consider the element in row idx, col idx position, sorry, you don't see it here, the code goes on. There is this part of the code that was not visible. So whenever you have the element in position row idx, col idx, you take that element, you divide by the sum that corresponds to that column, which is stored in this position, and then you put the result back inside the matrix. Okay? So this is the naive that I hope those who did this did something similar to this, I guess. Yes? No? Similar, not maybe exactly, but. Now, let's see how to do it in the numpy way of doing things. To see it, let's go back to how we split the problem, and that's the reason why we split it in this way. We said, first step, we have matrix M, and we want to compute the sum of the elements of the column of matrix M. What is the sum of the elements of the column? Well, the sum of the elements of the columns for the first column is this one plus this one plus this one. For the second element, I get this plus this plus this. For the third element, I get 1, 2, and 3. How can I represent it? Let's call this row 1, row 2, and row 3 of the matrix. What are the values of this array? These are exactly row 1 plus row 2 plus row 3. If I interpret this as vectors, rows, then if I add these 3 rows together, what I get? A vector that has as first element the sum of the first element of these 3 arrays. Then the second element will be the sum of the second element of the 3 arrays. The third element will be the sum of the third element of the 3 arrays. Exactly what I was saying before. So the sum of the columns of the elements of each column of an array corresponds to the sum of the rows of that matrix. If I sum the rows of a matrix, the result is a vector which contains in each position the sum of the elements that are in the corresponding column of the original matrix. But we saw yesterday how to compute the sum of the rows of a matrix. We said yesterday that if we use the sum method, The sum method computes the sum of the elements of a matrix. But if we pass an axis, it will perform the reduction over that axis alone. So if I pass axis 0, it will sum over rows. So we sum with an index that will scan the rows, and we sum the rows. Summing the rows corresponds to an array where each element is exactly the sum of the column of the elements of the corresponding column in the array. So if I sum the rows, each of these sum is obtained by reducing the corresponding column, because I'm summing the rows, so I'm reducing the elements of the rows. So each column of the sum is the sum of the elements in the corresponding column. Okay? I know that it's a bit tricky because you have row, column, column, row, and so on, but try to say it slowly. The sum of the rows of the matrix will give me an array. In each position of this array, I will have the sum of the elements of the corresponding column in the original matrix. Which means that my array sum can be directly computed by doing m.sum of 0. That is the array that contains the partial summation corresponding to the different columns of my matrix. So I have my matrix M, and the matrix, let's call it S here on the slide, this S, or S if you want, this one, which contain the sum of the different columns. Now the last step is normalizing the elements of the matrix. What do I have to do? I have to divide the element of each column of the first column by 5, the element of the second column by 10, and so on. Let's look at it from the point of view of the rows of matrix M. This first row is divided by what? 5 and 10, and then whatever is, let's say that here was 15, I don't remember how much it was, but let's imagine this was 15 and 20. Then I would divide this element by 15 and this element by 20. For the second row, I would divide the first element by 5, the second element would be divided by 10, then the second element would be divided by whatever was here, let's suppose it's 15. The fourth column would be divided by the fourth element of the sum. I don't remember what are the actual sum, but what matters is, what do we see here? Each row is obtained how? Taking the original row of matrix M, and then each element of this row is divided by the corresponding element of vector S. This is the definition of element-wise division. Each element of row 1 is divided by the corresponding element of the vector of sums. And I need to repeat this operation for all the rows of matrix M. How do I repeat all these operations? Again, I remember what broadcasting is doing. If I have matrix M and I divide it by a row vector that contains value 5, 10, and whatever else, then this vector is going to be used to do element-wise division of all the rows of the matrix. Broadcasting will replicate this vector 3 times, because we have 3 rows, and then it will perform element-wise division, which means that the first column will all be divided by 5, the second column will all be divided by 10, the third column will all be divided by the third sum. Or, equivalently, the elements of the first row will be element-wise divided by the elements of the sum array. The elements of the second row will be element-wise divided by the elements of S, and so on. So we just need to ensure that this is a row vector. But we said that in broadcasting, if we don't reshape, everything works correctly. So actually, we don't, row vector is 1 and then shape. So this is the first solution. Compute the sum and then reshape it. Divide M by this array of sums. This will allow, through broadcasting, to apply the division of each element, or each column of M will be divided by the corresponding element in the array of sums. Since when we broadcast a one-dimensional vector is treated as a row vector, and since sum of 0 removes one dimension because it's doing a reduction, so the output of sum of 0 is a one-dimensional vector, we don't actually need even to reshape in this case. But it's better to do it. Why it's better to do it? Because we can see exercise C. Exercise C requires to do the same thing, but this time normalizing the rows. If you write it naively, you don't have the solution, but it's just a matter of exchanging the role of column indices and row indices, then there is nothing particularly more complex than the solution that we have seen. We can do the same using numpy to do what? Compute the sum of the elements of each row, so reduce over column. The sum of the elements of each row is obtained by summing the columns as if they were vectors. If I sum the columns of this vector, then the result is a vector where in the first place I will have the sum of the first component of each column, so the sum of the first row of the matrix. In the second position, I will have the sum of the second component of each of these column vectors, so it's the sum of the elements on the second row, and so on. So I need just to do it on one, but this time, when I do the normalization, I need to divide by a column vector, because this must be applied to all the columns of my matrix. Now, since sum returns a one-dimensional vector, I need to explicitly transform it as a column vector, because otherwise, if I don't transform it, it would be treated as a row vector. But as a row vector, it would not work with what I want to achieve. So in this case, I must implement it as a column vector. Then, last thing, since we have 1 minute left, we can see, reasoning a bit, that exercise C is actually exercise B implemented over the rows. But what does it mean to normalize the rows of a matrix? Well, if I take this matrix and I transpose it, then I can normalize its columns. And I get a normalized matrix where the columns are normalized. If then I retranspose the matrix again, what I get is the original matrix with the normalized rows that corresponds to the solution of the previous problem. Now, it's a bit more complex. I leave you to think about this, but in general, if I have a problem that operates on the columns of a matrix and I want to operate on the rows, I can simply transpose the matrix, operate on the columns of that matrix, and then transpose the results. That's effective as if I were doing the same operation over the rows of the original matrix. So this is just one trick that I can use if I wrote a solution to exercise B to avoid writing the solution to exercise C. Again, I don't expect you to come with this kind of solution directly, but it's better that you start to understand how these things work. Okay, I think that's enough. See you on Friday, on Thursday. Sì, un ottimo suono.